Yeah, I'm excited to be here. I was telling Bhavna that all the smart people have been sort of congregating at AI2, and I really wanted to see what was going on here. So thanks for having me. Yeah, so I'm going to, there are a lot of models for knowledge graph construction and knowledge graph work, but I'm going to describe our particular flavor. And I know you guys know most of this, but let's do a quick review. So 20 years ago, I was a teenager. The World Wide Web had roughly 1 million pages. No one had heard of the semantic web. And right now, you basically give someone a quarter and you get a server. That was not the case 20 years ago. And now we have hundreds of billions of web pages. There are all of these ontologies. You've probably seen that linked open data graph a billion times. And now everyone has a smartphone. You can get servers very cheaply. And so we're in this landscape, and what we want to do is create structured knowledge. That seems to be the key to a lot of what we want to do. When I say structured knowledge, I mean a knowledge graph where we have entities, relationships between these entities, as well as some ontological label information. Okay, so when I say knowledge graph, I mean structured representation of entities, their relationships, and their labels. And so I'm going to go through my approach to knowledge graph identification, work I've done in scalability, and work I've done in streaming inference, which I think is essential in this talk. So we've come a long way in artificial intelligence knowledge, right? So you can type in something like New York Giants, and you get the latest scores. You get a little Wikipedia entry. You can even ask very esoteric questions to your smartphone, like, what sort of Pokemon is Pikachu? This is like before Pokemon Go, by the way. This was like, a few years ago, and it's still new. Pikachu is electric. And even in your social network, you can make these structured queries about, how you are related to people and the type of, the type of media you want. And there have been two approaches to knowledge graph construction. So the first is that you have all of this data on the internet, and you build these tools, ontologies, make it really easy for people to annotate that information. And now you're going to use those annotations to build a knowledge graph. And then the second approach, which has become very prominent, is the NLP information extraction approach, where you have that same internet resource, and you're going to do parsing, tagging, semantic role labeling, morphological patterns, and use all of this NLP technology to do the same thing. And the problem is that despite both of these approaches having their merits, they have some limitations. So if you look at the same kind of slide, well, the New York Giants are a football team, but you can see right here, there's a pitcher throwing a pitch, and it's actually the San Francisco Giants that have been surfaced in this, in this query. And you can ask about Mount Everest, and Siri is just confused about what Mount Everest is. Like, it knows it's a place, but then it doesn't want to tell you anything else about that place. And in particular, I love this giant story because it really shows you how difficult this problem is. So if you walk to AT&T Park in San Francisco, you'll see this beautiful mural, New York and San Francisco Giants, and you'll see the championships they've won. Well, the New York Gothams existed from 1883 to 1885. Somebody thought they should be called the Giants, so they became the New York Giants, a baseball team. Then somebody started the New York Giants, a football team, in 1925. And then in 1958, the Giants moved to San Francisco. And now, they're both a baseball team in the National League and a football team in the National Football League. And how is your knowledge base going to figure this out, right? This is the sort of problem that you guys are probably frustrated with every day. It's very complicated. And so we really want to really hit this roadblock where if you have the semantic web approach, it just doesn't scale. You have billions of web pages, and if you want to annotate them manually or even using some tools, it's still this Herculean effort. And so you hit this wall where your annotations have a low coverage. But the NLP approach has its own issue. So there's a lot of noise on the internet, and so the knowledge extraction tasks are not simple. They're very difficult, and despite all of the gains, there's still a loss of precision, which in the end, pollutes your knowledge graph and leaves you with many errors and inconsistencies. And so what we want to do is kind of straddle this, this gulf between the semantic, clean but limited approach and the NLP, very powerful but noisy approach. And the case study we're going to use is NELL, and I'm sure you're all familiar with NELL. It's at CMU. It's a large-scale information extraction project. It reads the web every day. It has a known ontology, which you see on the right there, which is fairly rich. And it has a knowledge base with millions of facts, and it's fairly public. It tweets every day facts that it's found. Lots of people use this data, and it's easy to download. And so NELL makes mistakes. And so these are sort of the types of mistakes you would expect to see in a knowledge graph. And I'm going to point out the three principal types that we see. So the first are entity co-reference errors. So for example, there's Kyrgyzstan, which is a country near Russia. And if you look at the NELL knowledge base, there are many, many variants of Kyrgyzstan. Some are misspellings. Some are more official forms. So you have Kyrgyzstan, but it's misspelled with alternately spelled with a Y, an I, an HY. And then you have the Kyrgyz Republic, which is what, what Wikipedia believes you should call Kyrgyzstan. And you can see these all show up in natural web text. So all of these forms refer to the same entity, but we don't necessarily know that in our knowledge base. So there's this entity ambiguity problem. You also get label problems. So you extract relations, but they're not always right. So NELL uses patterns where on this web page, all the links are birds. It's a birding website. Everybody posts links to the birds they see. And then one person screws it up. They show up, and they list the places they saw birds. And now NELL thinks Kyrgyzstan is a bird, because everywhere else, the links are birds. And the last are, the labels, relations. So if you want to know where Kyrgyzstan is, there are a lot of patterns. And some of the places NELL thinks Kyrgyzstan is are Kazakhstan, US, and Russia. And they're all sort of reasons. You can look at the provenance and see why these errors exist. But at the end of the day, you have this issue that these relations are, are somehow contradictory. It can't be in all of those places at once. And so I argue that these are all violations of ontological knowledge. And so in the first case, we had co-referent entities. And if we had the same as knowledge from an ontology, we could realize that Kyrgyzstan and the Kyrgyz Republic are really the same place. And the facts about them we can combine. The second type of ontological knowledge is mutual exclusion. If we know that an entity cannot be both a bird and a country, we wouldn't have this problem where you have bird and country in your knowledge graph. And last, we have selectional preferences of relations, which add some coherency. So if we knew that a country could only be located on a continent, we wouldn't believe that Kyrgyzstan is located in the US or it's located in Russia.
Can I say quick?
Yeah.
So the second one is a little bit harder, right? Because an entity can't be a bird and a country, but a lexeme can refer to both a bird and a country, and that's what you're recovering from the for web pages, right? So Java can be coffee in a programming language.
Right. So I guess there's this idea of where you go from a concept to an entity, right? So here we were talking about, there's this disjunct, right? Like here we're talking about tokens and trying to map the tokens to entities. And here we're talking about a single entity which has been dereferenced with the correct label. So you could imagine if you had a sufficiently deep knowledge representation, you could have Java programming language, Java food item. And NELL actually does this. It tries to do some simple concept clustering around tokens to figure out which one, which reference or which of the, what's the word I'm thinking of, which co-referent concept it refers to. And I've done some work on this as well, which is not in this talk, but trying to figure out that there's really two things. There's Java the coffee, and there's Java the programming language, and they're two separate concepts which we should keep separate in the knowledge base.
Right, I was just pointing out that you were saying that the issues you were showing earlier were due to violations of ontological knowledge, and I was just pointing out that you could have the knowledge of mutual exclusion between bird and country and still make that same mistake. You need something more than that knowledge to process that page correctly. It has to do with deciding that that's an error in the mapping.
Sorry.
I'll let you go.
Okay. Okay. So basically, the real issue is that when you have these types of ontological constraints, you have to build a joint model that looks at all of the facts that are in the knowledge base and finds these contradictions. And so when you build a joint model, it becomes difficult. To build something that's collective and looks at all the facts together poses a challenge. And so the research question that I explored mainly through my PhD thesis is, can we build these joint models to improve knowledge graph construction and remove some of the, combine both the natural language processing approach with the ontologies that we have from semantic web and other constructions. So the approach I introduced is called knowledge graph identification. And so first we'll go through the derivation. So we had this picture earlier where we had the internet, we'd do some knowledge extraction, and we'd get a knowledge graph. But we're going to revise that and say what we're actually getting is this extraction graph. And the extraction graph is going to be noisy. And now we're going to pull in the ontology to do, and joint reasoning to build a cleaner knowledge graph as a second stage on top of the extraction. And so that approach is called knowledge graph identification, and it builds on previous work in our lab called graph identification. And in graph identification, there were three big tasks. One is entity resolution, which maps to that first task where we tried to figure out what Kyrgyzstan is. The second is collective classification, where we were trying to label nodes. And the last is link prediction, which is finding the relationships between these nodes. And while we're going to perform graph identification, we're going to incorporate these ontological constraints, which we saw would be so helpful in removing the errors. And last, we're going to incorporate many uncertain NLP sources. So you could have a variety of different approaches that might be morphological or based on part of speech tagging. You could also use deep learning to generate some of these outputs. And we're going to use all of them as basically proposers of facts, and then combine them in this framework to decide which ones we trust and which ones we don't.
Quick question. So NELL had some idea of coupling constraints together as well. Is this, I'm trying to relate what they did with this version of constraints?
Yes, I guess there are like two lines of work. One is just, there's like the pure co-training approach, and then there's the ontologically constrained error rate work. So I'm not sure which one you're more interested in.
It was the second one.
Okay, so I guess, as I said, the second one, they have these sources, and what they're trying to figure out is how much we trust them using the ontology as a way of constraining them. And here, we're trying to actually infer the knowledge graph. So I think the goal is, build the best knowledge graph or figure out how much you trust. And here, you're kind of getting the bonus because we're going to learn weights for the for each extractor while we're building the knowledge graph. So you kind of get both of them at once. But we don't, I feel like that work on the error rate bounding, they have a lot more theory. And so I think that theory gives you better guarantees on exactly what you're getting out of it. So you can know exactly what the error rate is. Here we're learning the weight as sort of a side effect. Okay. So let me sort of illustrate what this is going to look like. So we have these extractions which come from some NLP pipeline. And we're going to represent them as an extraction graph. So this is sort of the example we saw before. We have bird and country as labels. This is actually a slightly different relation, the capital of the country. And so we're using dotted lines here to show they're sort of uncertain. And the uncertainty is this 0.5, 0.7, 0.9, 0.8. These are sort of uncertainties that you might get out of your NLP pipeline. Then we're going to annotate this extraction graph with our ontological relation. So we know bird and country are mutually exclusive. We know the domain of the has capital relation is country. And so by adding these constraints in, we have we're going to constrain exactly the value of these relations. We're also going to include entity resolution information, which says that Kyrgyzstan is the same as the Kyrgyz Republic. And then last, we're going to run inference and try to enforce these constraints on the knowledge graph and get what we really want, which is this clean knowledge graph where the entities have been combined. We have a clean relation and a clean label, and we remove the spurious labels and spurious relations. So that's the high-level idea, but how do we actually model this? So we're going to build this probabilistic graphical model for knowledge graph identification. And what we're going to start with are each of these facts in the knowledge graph as a variable. So the label of Kyrgyzstan being a bird is a variable. The relation that the capital of the Kyrgyz Republic is Bishkek is a variable. And the first thing we're going to do is we're going to add priors from each source for each of these facts. So if you have multiple extractors, each of them is going to provide you with a prior. And a lot of the work that's been done previously just sort of stops here. They have logistic regression. They have their sort of inputs, which are these priors. They run logistic regression, and they're done. But we want to constrain these. So we'll add constraints for mutual exclusivity, which are going to relate the bird and country variables for each of these entities. We'll add constraints for the domain range selectional preferences, which will constrain this relation and this label. And we'll add same entity constraints, which constrain the co-referent entities to have the same relations and the same labels.
Question.
Yes.
Just getting back to the previous example with Java. This graph that you're showing right now is dependent on the fact that Kyrgyzstan is just one entity, right? And so how is that?
Yeah, so I think what you would have in the Java case, right, is that you'd have Java : programming language here and Java : coffee here. And now the question is, how good is your entity resolution? So if you have ontological knowledge for entity resolution, they might say these are different. Or if you have some automated process that's doing the entity resolution, it might have weak links here. And so if these aren't constrained, it's fine that one of these is a coffee and one of them is a programming language. So there are like two problems. One is how well you've done this concept clustering so you can separate the two. And then the other is once you've separated the two clusters, is your ontological knowledge or entity resolution system good enough to keep them separate and not merge them accidentally? And then if you can keep them separate, then you're all set, because these constraints will not trigger. And so you'll kind of get one subgraph, which is Java the coffee, and another subgraph, which is Java the programming language. And each of them will be independently consistent.
Right. But I mean, here, an alternative explanation is that Kyrgyzstan is a country with the capital Bishkek. It's also a bird, right? I mean, that's consistent with the data that you've shown. So somehow you have to make that less likely than the resolution that you showed a moment ago, in which one of these is just a false.
So why would it also be a bird? Are you saying that?
Well, what I mean is if the sentences you had were all the knowledge that you've gotten out of the web about Kyrgyzstan, you might think Kyrgyzstan, well, it could be a bird.
Right, and so so there are a couple things, right? So on the previous slide, we saw that bird was less certain than country, so that might help us. And the other thing that we saw is that if you know the capital is Bishkek, even if you didn't see the country extraction, this would let you infer country, right? So you could say, well, maybe I never even saw country, or country is less certain than bird, but because we're very certain that the capital is Bishkek, that's going to push up country, and that's what we'll actually end up inferring, and we'll throw out bird. And so I think this is the real strength of the method, right? So you might have some information somewhere else which propagates to what you really need to infer and excludes something that's.
Yeah, I think the question, maybe Clinton is a better example here, right? So Clinton has two main meanings, right? Hillary and Bill. And they occur, not exactly the same frequency, but both with high frequency. So the question is, if you run this type of model on the text mentions of Clinton, what would happen, right? Because sometimes it's this, sometimes it's that. It's very easy to create some sort of composite that says that Bill Clinton was Secretary of State, or right? Is that a fair?
Yeah,
yes.
A perfect bill.
Or another way to put it, imagine that there was actually a very rare bird called Kyrgyzstan.
Yeah.
Turkey is a good example.
Yeah, well, I think the Clinton example is better. The Turkey, I think, is still kind of close to Java because it's concept clustering. So I think the problem with Hillary Clinton and Bill Clinton is that they're both politicians, right? And so I think that's going to screw a lot of things up, because now there's a lot more potential for confusion. So I can see how where you have a collection of extractions, and one is a governor and the other is a senator, and you could see that you could say like a politician could be a governor or a senator. I could see that that is a much harder problem for this framework than some of the others. And so, yeah, I agree. It's hard, right? I think that's the reason you guys have jobs. I have a PhD, is that we spend all this time working on this problem, but there are still a lot of nuances. And even the San Francisco, New York Giants, right? I'm not claiming that I've solved that problem, but it's an interesting problem, and I think it's sort of what gets you up in the morning to say, well, one day I'm going to build all of the subcomponents that really will separate Hillary and Bill Clinton and change what is plausible for Hillary Clinton and Bill Clinton. And I think part of that is just we have more data now, right? So even if I think when you have less data, you get one page that says something and you extract it. And now maybe you need lots more web pages or lots more text or lots more video before something gets promoted or is part of the candidate pool. And then you can be a little bit more flexible with how you do things, because when you see Clinton, you've probably figured out that it's in the Hillary Clinton sort of cluster rather than the Bill Clinton cluster. And the price of that is obviously that long tail. If you saw something once, it might be really important, but only one person has picked up on it. So I'm sure this is kind of pedantic. You guys all know this, but I think it's interesting. I'm not going to claim that I have all the solutions. Okay. Right. So we have this probabilistic graphical model, and it's capturing basically the intuitions from the knowledge graph identification setup, but this is sort of a very grounded approach. And so how are we going to actually implement this graphical model? Well, our group at University of Maryland and now at Santa Cruz has been developing this framework called probabilistic soft logic. It is a templating language for hinge-loss logical Markov random fields. And we're going to specify a collection of logical formula. And the real trick here is that the logic is a soft logic. And so you'll see this tilde. That means this is not the logical and you know and love, but in fact the Lukasiewicz T-norm and co-norm, which have this relaxation of traditional logic. So in the case of an and, it is each of the conjuncts, their truth values summed, and then one is subtracted. So I'll talk a little bit more about why we've chosen this and what its nice properties are. But in particular, now when we have these uncertain extractions, we can actually represent soft information from an extractor, which thinks maybe the label is 0.5, in which case the truth value is going to be relatively low. Whereas if the label has a higher truth value, then we're going to be more certain about this consequent. So I'll walk you through a little bit of this. So, okay. So what we're going to do in our, I may have reorganized my slides. Okay. So what we're going to do in the model is we're going to incorporate a series of logical rules, and those logical rules are going to capture what we want to say about the model. So what we're going to have, these predicates relation and label are what the true relations and the true labels that we want in our knowledge graph. And we'll have these candidates, and the candidates will come from some technique or extractor T, and they'll have a truth value based off of the certainty of that extractor. And we might do some calibration to make them closer to truth values and not just random numbers. And then we'll have a weight for this, which gives us our confidence in this extraction technique. We'll have rules for entity resolution, and the rules for entity resolution, we're going to have the same entity predicate which captures coreference, and then we'll have rules which say coreferent entities should have the same labels and the same relations. And last, we'll have ontological constraints. So we'll have relational inverses, selectional preferences like domain and range, subsumption of relations. So if you have relation R, and S subsumes R, then if you have R, then you should have S. Same thing with labels. If P subsumes L, then if you are an L, then you should be a P. And then mutual exclusion, like bird and country. And so we're going to take all of these rules, and we're going to put them in PSL, and then we're going to ground them. And I assume most of the audience is familiar with this, so I'll go through it quickly. But you're going to take this template rule, and you're going to substitute in constants for the literals, and you're going to get a ground rule. And so now you have Kyrgyzstan and Kyrgyz Republic are same. Kyrgyzstan is a country, so Kyrgyz Republic should be a country. And now we want to determine what is the value of this grounded logical formula. And if it were, again, regular Boolean logic, it would be very simple. This could be a 1, this would be a 0. You can infer either 1 or 0 for this. But since it's soft logic, the rules have changed a little bit. So we have this conjunction in the body of the rule. And let's say this has a truth value of 0.9, this has a truth value of 0.8. Well, we're going to take the max of 0 and the two conjuncts minus 1. So the value of the body of the rule is 0.7. Is everyone good on this? OK. And now we have an inference problem. So we know the body of the rule is 0.7. What is the value of the head? We want to actually infer whether the Kyrgyz Republic is a country. And so if you have implication, you're going to take the body minus the head plus 1. So this is going to be, head minus body. So this is going to be our unknown value minus 0.7 plus 1. And what that looks like is this sort of upside down hinge loss. So if your value is less than 0.7, you're not satisfied. And the lower you go, the less satisfied you are. And if you're above 0.7, then the rule is satisfied. You have a satisfaction value of 1. And what you want is to satisfy all your rules. And really what we want to do is if we turn this into a loss, we're going to subtract 1 from this. And it's going to look like a hinge loss. And we're happy with the hinge loss because the hinge loss is easy to optimize. And lots of work has been done on this. And so what does that hinge loss mean? So in Boolean logic, if you have a Markov logic network, we know exactly what we're getting out. They're worlds, we count them, we get some satisfiability. Well, Gomez and Williamson in 1994 had a continuous relaxation of maxsat, which looks a lot like this. And it's a randomized algorithm where you relax your outputs in a maxsat problem to the 0-1 interval. You infer using a linear relaxation. And then the value you get out, you treat as a rounding probability. So you flip a coin with a bias equal to the value you got out of that continuous relaxation. And this is a 3/4 optimal solution to the maxsat problem. So there's an optimality bound on what happens when you do this continuous relaxation. And my colleague Steve Bach at Maryland actually showed an equivalency between the Lukasiewicz norm and conorm to this rounding formulation for maxsat. So the takeaway is that when you get this output, what you're really getting is this rounded maxsat output. And if you use that maxsat rounding, you're going to get a bounded quality on the output of this, assuming you have good logical inputs.
Sorry, so doesn't the third bullet about the bounded quality follow from the first bullet? I don't understand what we learned from the norm and conorm being equivalent to the maxout.
Well, I think this work existed, and the formulation, the linear relaxation, no one had said, oh, that linear relaxation is exactly the relaxation you get from the norm and conorm. Because you could have there are definitely other soft logics. So you could throw in some other soft logic and you wouldn't have this bound. So all I'm saying is that the soft logic we have chosen for our relaxation is the same is equivalent to the soft logic, or the relaxation that we've done for maxsat. And because they're equivalent, you get the bound. If we had chosen a different soft logic, we don't know what's going to happen, and probably not going to be convex.
So I should read this 2015 paper, but the Gomez and Williamson, that gives you optimality gap on the maxsat objective function. What you're trying to infer is probabilities. They seem like very different things. Like the bound on 1 seems to have nothing to do with bound on probability as opposed to how far you are from an objective function.
Right. I guess at the end of the day, so I guess you can kind of look at it through either lens. So what we get out is something continuous valued. And the continuous value is proportional to the rounding probability. So you could keep it as the probability, but really what we want at the end of the day is probably a discrete knowledge graph, which says this is true and this is false. So you could also round and get this discrete graph and say this is how we have a 3/4 bound on satisfying all of those rules about Kyrgyzstan and birds and countries. Or you could say, well, this confidence, let's keep it native and treat that as our confidence in the fact. So, OK. So hopefully, we have this nice framework. It's convex, and we get something with a bound and some rigor to it. It's not just some random number that we've come up with. So hopefully that's good. And so what we're going to do with all of these, we have our groundings, and we're going to, each of these variables in the knowledge graph is going to be a variable in our probability distribution. We're going to condition on the extractions and other evidence we have, and then we're going to build this exponential model where you have a weighted sum of these potential functions. And so each of these is an extraction of the knowledge graph. The weight here, this is the set of all ground rules, and this is one of those ground rules that we've seen, like the same entity, Kyrgyzstan, Kyrgyz Republic. They're both a country rule. And then the weight we're going to learn from training data. And then the potential value is actually that satisfaction we just saw, or the 1 minus the satisfaction that we saw on the previous slide. So basically, we're going to try to keep all those hinge losses at 0 with some weight. And that's going to be our energy function. That energy function is going to give a probability distribution over all of the possible knowledge graphs in this continuous space we could have. And so we're going to run inference, and we're going to find the maximum, the graph that maximizes this probability distribution. And just to illustrate that, as you can see, these are the rules that sort of go into the groundings, and this is what we're optimizing over. So these are all our potentials, and we want to minimize some loss function to get as many of them true as possible. And when you move this back into graphical model land, each of these green boxes is a fact, and each of these potentials is creating a dependency between these facts. So the candidate extractions are these sort of potentials like F1, which give a prior to a fact. We have these, let's see, so we have these priors on labels, we have these priors on relations, we have the same entity constraints, we have the domain range constraints, and we have the mutual exclusion constraints. And they're all part of this large graphical model which we're going to build and then optimize. So what happens when you do this? So we have a couple experiments I'm going to present. So the first is on linked brains, which is a linked open data version of music brains. So they take the data that this community provided, music community sort of adds facts about artists, albums, songs, and they have a music ontology which they overlay on top of that. And then since that data is, we assume to be clean because it's human annotated, we add some synthetic noise. The other data set is NELL. So we have roughly 1 million extractions which come from various natural language processing on the CLUWeb corpus, and there are roughly 1 million extractions. The ontology is much richer, and we use NELL's existing ontology. So first, looking at this linked brains, we'll sort of do a ablation study, or sorry, a factorized study where we look at entity resolution and the ontological rules and see how much they contribute. So the baseline is just using those truth values in sort of like a regression framework. And in entity resolution, you can see we get a gain. In AUC, in using the ontology, we get a gain. And when we put them together, we get sort of the best of both worlds. So adding all of the rules into this model kind of gives us the strengths of each of them in this convex formulation. So for NELL, we're going to look at 2 different evaluation settings. So there was some previous work that used a discrete MLN for the same knowledge graph task, and they had a very particular model. So it's a closed world model where they enumerate the facts that they're going to infer in their test set. And when they enumerate these facts, they sort of do a 2-hop neighborhood around their test set to get the context. But they'll exclude things that are contradictory to the test set. So if something's mutually exclusive with what they have in the test set, they won't actually infer that variable or allow that variable to be inferred. So that sort of sort of gives an advantage to the method and handicaps the actual results, because you're explicitly saying if it's contradictory, I don't want to think about it, which is not really how you'd expect any real system to work. So it excludes trivially satisfied variables. So we also have a more realistic setup where it's open world. So anything that comes remotely from the test set is included. So we infer all possible entities, relations, labels that you could ever get from the evidence, including things that are contradictory, that are supported by some sort of extraction. And now we're going to get a truth value for all of these things. So in the first setting, this closed world target set model, the baseline is actually just the confidences. NELL does slightly worse than the baseline because they have sort of a heuristic way of ensuring consistency. So if they get something wrong in the knowledge base and they continue adding new things, they'll actually throw some of those new things out because they're inconsistent with potentially an incorrect fact. The MLN in this previous work does better than both of these, but it's not really that much better than the baseline. And we improve a little bit on this in this target set. The real win here is that since we have this convex formulation of knowledge graph identification, this takes 10 seconds for 25,000 facts. So normally the bottleneck when you get an MLN is it's going to take forever, and you have to run Gibbs sampling, and sometimes it doesn't converge, or you get bad results, and it's this like black magic. Here it's a convex formalization, so you don't really have to worry too much about parameters. Mainly, you're going to get your output and you're going to get it fast.
Quick question.
Yeah.
So the reason the MLN doesn't do so well, is that because it's finding a suboptimal solution, or is it because you're injecting some extra knowledge in your formulation?
The only additional knowledge that we have, well, we have a little bit of additional knowledge, which is entity resolution. So their model was not knowledge graph identification. They basically threw in some of the ontology. So we added entity resolution, which helped. They also are not doing soft truth values, right? So they might have a little bit of a loss there because they have to basically count possible worlds. And then again, it's not, so we have an exact optimization in a continuous space, and they have a sample, they're sampling in this Boolean space.
But if you ran the MLN for infinite amounts of time, you still wouldn't expect it to be as good, is that right? Or you don't know?
If you had infinite amount of time, maybe you could optimize that satisfiability formula, right? So I guess it kind of comes down to what we want to do is optimize that satisfiability. And we know this is 3/4 optimal. You could somehow imagine getting full optimality if you had infinite time. But given how complicated that space is, you're probably not. Okay. And then we went where MLNs can't go, which is this open world knowledge graph. So NELL will show the same results because NELL actually has this open world formulation. It doesn't really exclude anything from its target set. And so we're handily beating NELL on this. And our inference time is a little bit over 2 hours on sort of the hardware of a few years ago. And it produces 4 million facts from the 1 million extractions that we started with. So it's actually inferring a lot. And so just to sum up what happened in this section, we have this knowledge graph identification model, and we're going to take that concept and implement it using a graphical model with a probability distribution over knowledge graphs, and we have great results on 2 knowledge graphs. Okay, so I've told you about this. I think the real challenge in a lot of knowledge graph work is scalability. So 1 million extractions is fine. How do you get to 1 billion? And so right now, we're fast in the sense that 10 seconds for 25,000 facts, about 2 hours for 4 million facts, and we have roughly 30 million ground rules or constraints in the model. But we know in the end, this problem is going to be somewhat intractable, right? So we know that this is NP hard, and we're trying to solve maxat. We know that the actual state space is 2 to the number of facts if we're thinking in Boolean terms. And we know the ground rules are going to basically grow at based on the rule length and the number of candidates we have. And so we've kind of discussed how we fix some of these, right? So it's an NP-hard problem, but we know this 3/4 optimal solution exists. We know the state space is huge, but it's convex, so we don't have to explore the entire state space. What we're stuck with is that the rules are going to grow, or the ground rules are going to grow as we introduce more facts. And so I think this is the big challenge that all of these logic-based systems are going to face. As you have longer rules and more complicated rules, you're going to have more and more ground rules, and you're going to have to do something about it. And so that's what I'm going to talk about in the next couple sections. So this is a graph of knowledge graph identification runs over 1,000 runs, and this is like a scatter plot of the number of optimization terms and the running time in seconds. And you can see it's sort of messy, but you kind of get a linear fit or a fairly linear growth. So the good news is that the running time for knowledge graph identification in this convex formalization is roughly linear in the number of ground rules. And the main issue is that the number of rules is going to grow polynomially as we add more extractions. And so we have this huge knowledge graph. What are we going to do with it? Sort of the obvious thing, partition it. So we're going to cut it up into pieces and split it up over machines. So the main issue is that if you cut up the knowledge graph, you have smaller problems. You can run them in parallel, and you can, based on the size of the partition, get some speed quality trade-off. But you have some drawbacks. One is when you cut it up, you're doing some work. And that partitioning is going to become time-consuming, especially as the graph gets bigger. And the other issue is that what we saw in the last section is that what makes knowledge graph identification work are dependencies between the facts. And so if you cut it up, maybe you lose those dependencies. They show up on different machines. Now you're in trouble. And last, when you get something new, you may have to repartition. You don't necessarily know where to add it. And so maybe the best partitioning requires redoing all of that work. And so the simple solution to this is you partition the ontology. So you have sort of a graph that connects the labels and the relations together using the ontological formulation we've seen. So like the range of located in relation might be states, and the domain might be cities.
So let's consider the science domain. So based on this ontology, you would have some stuff for location and some stuff for animals, and they're going to be separated. But you have a lot of information about which animal is living in which location, and that's very important. So if you do this partitioning, you're going to lose all.
Yeah. So hang on for like 3 slides, and then if you're still not happy, let's ask that question again. Okay. So we're going to cut up the ontology, and then we're going to get a partitioning based on the ontology, not the knowledge graph. And that ontology partitioning is going to partition our facts, and that's how we're going to partition across machines. So the nice things about this are the ontology is a smaller graph. The ontology is what we're using to build our model, so it's got all the dependencies. And when you get something new, you just figure out where that fact belongs in the ontology. You don't have to redo any work. So there are a couple of disadvantages in the naive approach. One is that it doesn't really care about the data distribution. If you have 1 million facts about locations and 1 fact about sports teams, it doesn't really know that yet. And all the dependencies in that graph were treated equally. So a domain is the same as a mutual exclusion, is the same as a subsumption. So we're going to handle these 2 drawbacks. So first, we're going to annotate each of the ontological facts with their frequency. So if you have 10 location facts and 15,000 city facts, we're going to put that. And now when we do the partitioning, we want every partition to have an equal vertex weight. So now that we've weighted the vertices based on their ontological frequency, we'll at least have a sense of the data distribution going forward and be able to optimize for that as well. And then the second refinement is that we're going to weight the edges based on some measure of importance. So if we see that there are very few subsumption edges, or subsumption has a high weight, we're going to create a high weight here in the ontology. Whereas if mutual exclusion has a low weight, or there are many, many edges, we're going to give it a low weight. And so now when we're doing the partitioning, we're going to take into account both the frequency in the ontology as well as the frequency of the facts in the extractions. So how do you feel about?
So I think that in that case you cannot do partitioning because essentially these weights and the links are so heavy that you can't really cut them. So basically you can't really do the partitioning on that specific, at least knowledge base. That's my feeling.
Yeah, I guess so. If you have, it depends on the size of your knowledge base, right? If you have a very small knowledge base, a small ontology, maybe everything sort of gets stuck together. But if you think of like a general purpose knowledge graph, you do expect there to be some clusters. And I agree, partitioning is always going to hurt you because you're throwing out some of those dependencies. But the question is, which dependencies are the best to throw out? And so I guess my argument is that this is probably better than sort of the naive approaches of just partitioning, doing a graph cut on the knowledge itself, or doing a graph cut on the ontology without any weight distribution information or weighting. So in your example, if you have animals and locations, if you set the weight of that to be high, then hopefully that's what's preserved. And if the weight of something else like animal and I don't know, like domestic or not or something is low, then maybe that's not as important. So I'm running out of time, so I'll go through this quickly. But basically, we tried, the basic ontology, the ontology with vertex weights, the ontology with vertex and edge weights. The edge weights actually didn't help that much, but we got the best performance with the vertex weights. So we take our running time for this subsection of knowledge graph identification from 97 minutes down to 30 minutes with 6 partitions. And if we draw it out all the way to 48 partitions, the running time drops to roughly 10 minutes per partition, which means that we took this thing that used to take roughly 2 hours and brought it to 10 minutes. And the really exciting thing is that the AUC doesn't really fall that much. So we go from like 0.794 to 0.788. So this might be that the problem is relatively robust to partitioning, but hopefully it also suggests that this is a better way to partition than the naive approaches where we did see the AUC fall a bit. So this is one approach to scalability, and now I'm going to talk about streaming inference, which is sort of my more recent work and I'm really excited about. So what you have in many cases is you have your knowledge graph and you add new facts to it. And now the question is, what do you do when you have these new facts? Do you rerun inference? Or do is there something smarter you can do? And this is not just a knowledge graph problem. So you have recommender systems, you have gene networks, you have knowledge graphs, you have collective classification. And so somebody rates a new movie. What do you do with your recommender system? Or somebody, so this might be a good recommender system model. So you have some new information, and now you have to update your recommender system. The same thing goes for social networks, right? Somebody new joins your social network. What do? Do you rerun all of your link prediction tasks for your social network, or can you do something smarter? And so there are all of these relational models that we've developed for collective tasks, and we often have millions of users, thousands of movies in recommender systems. We've seen millions of facts and thousands of ontological constraints in knowledge graph, millions, even billions of users now on social networks. And every time somebody joins a social network or rates a new movie, you don't want to redo all of the work in your collective model just to update potentially a few of the facts. And so you might ask, why not repeat inference? Well, we want this rich model, and if we have billions of facts, it's going to take hours to run the model, even for fast models like the ones I've presented. And really what you want is inference to take about as long as your new facts come in. So if you get a million new ratings a day, you want to incorporate those million new ratings and infer them over the course of a day. And by the time the next day starts, you're ready for your next batch of updates. And we have this intuition, which is that we're basically doing the same thing over and over, right? We're not going to change most of our network. There are only a few things that we really need to update. The San Francisco Giants are still going to be in San Francisco. They're still going to play baseball. We don't need to revisit that every time we get a new fact. And so the problem setting is that we have these large graphical models, and we have changing evidence. And instead of repeating inference, we're going to partially update our inference result. And the real question is, we have a map state, the maximum a posteriori state that we've inferred, and we want to update it in some approximate way without performing all of the work of inference again. And so there's a slide missing. But so the question is, can we do this? Is this even possible? Can we update inference? So imagine you have like a cliquey high school network where everyone wears the same color to class every day. And so you might start out with very non-informative priors, and you'll assume everybody is going to wear blue. And now you might fix some of those, so if you have full inference and you see somebody wearing red, you know everyone's going to wear red. But if you do partial updates and you fix some of these to be blue, even if you see someone or have strong evidence that someone's going to wear red, you can't update, because that's going to create this inconsistent state. So you fix some things to blue, everyone has to wear the same color, everyone's going to wear blue, even when you start seeing evidence for red, right? So in the general case where you have a discrete model with constraints, you can't do this. And so we're going to look at a slightly simpler model. So we have a fixed model. The dependencies and weights in the model, in the graphical model, are already known. But we get new evidence and new observations. And the variables are going to stay the same between epochs. And now we have a budget. So we have to fix some amount of our previous inferences, and we only get to use our budget of new inferences. And we're going to use something like probabilistic soft logic, where we have a strongly convex inference objective. And so there are two big questions that we have. One is, what guarantee can I give you in this setup? If I have some budget, how much will I regret the inferences I choose and the inferences I fix? And what should we infer? So you get to choose m things. Which m things should we infer? So what we're going to do is define this notion of regret for this online collective inference setting. And I'm going to introduce regret bounds for the particular class of models we're using, strongly convex inference objectives, like PSL. And then we're going to develop some algorithms to activate your budget worth of variables in a smart way. So first thing, regret bounds. So generally in inference, we're estimating the probability of y given x. In online inference, we're going to fix some set ys and infer the rest ys bar. So everything that's not an s gets inferred. In online learning, regret is how far you are from your optimal update. In inference, we're going to say how far is our approximate inference from the full inference we would do, where we'd infer all of the variables, not just ys bar. So we're going to define regret as the distance between full and approximate inference. And here we're taking the L1 norm over n variables. And so here, full inference is just h of x given w. And the approximate inference is just is h of x and ys given w. So you can see here we're fixing ys, and we're only inferring ys bar. So we're conditioning on these, and ys bar is what's left over. And h of x is just our energy function with a prior. OK, so this is the regret bound we developed in this UAI paper. So the ingredients are the Lipschitz constant for our energy function, the 2 norm of the model weights, which are the weights of the rules, which are generally pretty low. The prior weight is in the denominator. And really what we have, so basically this is a constant, this is a constant, this is a constant, this is the number of variables. So all you're really left with is the distance between what you've fixed and what its optimal value would be if you hadn't fixed it. So if this distance is low, you're doing pretty well. You have low regret. If this distance is high, you're in trouble. So if you do a good job of fixing ys, you have low regret, and you might as well do partial inference instead of doing full inference. So we looked at this in a few different models based on how much collective inference there is. So the higher the rule weights and the more collective information, the closer the variable dependencies are tied, the higher you'd expect the regret to be. So the dotted line is the regret bound, the worst case. Blue is when you have a lot of relational information and collective dependencies. Red is when everything is local and you have low dependencies. And this is sort of what happens if you just fix your inference result as you continue seeing new evidence. The longer you wait to update, the more your regret is going to be. OK, so as I said, the real question is, how do you fix things? And so what we're going to do, so what we're going to look at is that this problem is actually the knapsack problem, so we know it's NP hard. But what we intuit is that we want to fix the variables that won't change. And then the question is, how do we know what's not going to change? And the approach and hypothesis we have is that using what happened in the past will give us an idea of what's going to happen in the future. And so we're going to explore this from the lens of consensus optimization. So how many of you are familiar with ADMM? I see like half. Okay, so we're going to go through this quickly. So in ADMM, you have your potential functions from our energy function, and you have the variables. The variables belong to one or more potentials, and we're going to, normally we would try to constrain these and infer them collectively, but in ADMM, we're going to break this up into separate copies of each of the variables that are local to each of the potentials. Now we're going to optimize each potential locally and try to get them to agree on the value of the variable. And so the particular way we're going to do this is that we're going to introduce Lagrange multipliers on this consensus constraint. So we have a constraint that all of these copies agree on the value of y2, and when they disagree, we're breaking that constraint, so we penalize it by updating a Lagrange multiplier, or updating sort of a penalty term using the Lagrange multipliers. And so in our objective, we have the weights of the potentials themselves, which are the losses, the consensus value we've inferred, and the Lagrange multipliers. And the intuition, we're going to propose two approaches. So the first one is that the value that we get in the soft logic formalization is going to be important. So if we think of uncertainty sampling, anything that's near 0.5 we're uncertain about. That's a good candidate to infer again. And the slightly more nuanced is that we're going to use the Lagrange multipliers, which are variables which violate this agreement constraint. So there's disagreement about this variable. We don't know what its value should be. One person's voting one way, another's voting the other. Let's infer that again. Maybe we can resolve that disagreement. So we use the rule weights and the Lagrange multipliers to get a utility value for each variable. And so the last sort of modification we have is that we're going to use the relational structure as well. So we're going to seed based on the new evidence that we get. So if you see, for example, this is an updated value, we're going to look at the graphical model around this variable for which we've gotten new evidence, and then use the utility function to give each of the variables a weight, but also attenuate it based on a decay from the distance of the new evidence. So if we see a new evidence here, we walk the graph, and if you're really far away, even if you have a high utility value, it's going to attenuate. And if you're really close by, even if you have a low utility value, we're going to keep it. We're going to preserve it. So some experiments. We have two data sets. One is synthetic collective classification, and the second is collaborative filtering on the Jester. So in Jester, you have users rating jokes, and you get more ratings on jokes as time goes on. In collective classification, you're trying to infer some label of users based on their friends and other social network information. So I'll skip this. So basically what you get is so we have three different approaches. So the dashed is the do nothing, don't update inference ever, and you can see that starts growing. So your regret is going to grow over time if you don't do any updates, because you're fixing everything. And that sort of is shown by our bound. We have a random baseline, which is actually pretty good. If you randomly pick things to optimize, each round, you're going to reduce your regret, and it's going to start going down over time. The two blue lines, one is the Lagrange multiplier approach, and the dotted line uses relational information on top of just the Lagrange multipliers. And you can see they do the best. And the sort of uncertainty sampling near 0.5 does not do that well on collective classification. And then this is the actual, so this was regret, which is difference from full inference. And here you see the actual error, and it's lower bounded by this black line, which is full inference. But again, the blue lines, which are the Lagrange multiplier-based methods, do fairly well. And so the error approach is full inference, but there's a 69% reduction in inference time when you do partial inference updates. And then this is the collaborative filtering. We set a budget of 25% and 50% of the variables. You see sort of similar curves here. So on the top is regret. Regret goes up if you do nothing, but stays low if you do the Lagrange max or in this case the random. But the really interesting thing here is that the error, the root mean squared error here is very low for uncertainty sampling. So these are things which if the intuition we have is that if you fix the polarized ratings, you're going to get you're going to actually preserve some really interesting information, and the things people are sort of lackluster or sort of neutral on are what you really want to infer. And so again, we see a large reduction in inference time. So just to summarize, we have these regret bounds for approximate versus full inference. We have a formulation of regret bounds which depends on the error of your fixed variables, and we use ADMM to optimize this. So I'm out of time, but basically I talked about knowledge graph identification, the regret bounds, and scalability, and there's lots of future work. So I think the streaming inference is where the future is for a lot of knowledge graph completion, so adding new variables and doing that more intelligently. This is also an idea for active inference, so if you're going to get labels, which labels should you get? And finally, there's a lot of orthogonal methods, tensors, neural networks, random walk proofs. All of these can be incorporated into our framework and trying to kind of get the best of all possible worlds. And thanks to all of the great collaborators I've had.